Okay, so welcome back to sketching some more exponential graphs. The skills required to be able to understand the concept in this video is to understand what the parent function looks like. This is done by understanding positive exponents, zero exponents, and especially negative exponents. If you don't know what I'm talking about, please refer to episodes 4 and 5 of this series. We'll help you with these exponential parent functions. All right, so let's sketch these two graphs, which are parent functions. And if you need more time, pause it right now and check yourself. The nice thing is, regardless of what the base is, except when the base is 0 in a calculus course, that's a problem. We pointed that out before. Is that the y value is 1, 2 to the 0 is 1, and 4 to the 0 is 1. They share that point in common. That's very powerful for these parent functions. The other thing is that negative exponents get closer to 0, and positive exponents grow without bound. So let's see what, remember that parent function looks something like this, of the form it grows without bound, and it has some nice curvature getting closer. Let me redo that one. Getting closer and closer to 0. That means there's a boundary line, and it's an equation of a line. What's the equation of that line? Y equals 0. Remember that this is not like the line of symmetry for parabolas and quadratics. Same idea applies here, but because the base is 4, it's going to grow faster without bound. Maybe I should try this type of curvature. There we go. Whoops, I didn't like that one very much. Something like that. And we know the boundary line, it is still y equals 0. It still grows without bound. And that's two examples of the parent function, all right? Remember, they're in the form y equals any base, letter a, to the x, with some exceptions. That means that the base, a, is going to be greater than 1. In future lessons, we will explore what happens when the base is less than 1. For right now, we will focus on greater than 1, like 2, not bases like 2 or 4 or 5, 7, or 3/2, okay? So then what are the 3 key features of these graphs? Number 1, I don't know in what order it jumps out at you, but in any order is fine. One of the things that I find the most powerful is that common y-intercept. For right now, I'm going to call it a common point, because sometimes it is transformed. Common point. In this point, it is the y-intercept. So I'll put that in parentheses, because that's not always true. And what is that point? 0, 1. Regardless of what the base is, as long as it's greater than 1. All right, number 2, the other thing that jumped out at me is that in common, they have a boundary line. Boundary line, and what is that common boundary line? It is y equals 0. So what else jumps out at you compared to other graphs we've done before, or maybe even similar? I remember when we explored the quadratic equations, those graphs have curvature. So same idea here. These graphs curve. They have curvature. And in this case, it is curving upwards. They're curving up. They don't always curve upwards. But when they curve down is because it is a transformation, all right? Which we might encounter in this video. Understanding these 3 key features of the graph will allow us to transform future exponential graphs in a more efficient way. So let's apply those ideas hopefully in this video. So look, we have sketched the graphs of 3 to the something, and then its negative version, negative 3 to the something. So notice in this case it is like this. If you need to see the parentheses, this one implies negative 3 to the x. I'm going to remove those, but that's what it is. And same here, negative 2 to the something. Excuse me. So we know this is a parent function with a y-intercept or common point of 0, 1. And we know that when exponents are negative, it gets really small, closer to 0, which gives us the boundary line of y equals 0. And when the exponents get more and more positive, this grows really fast without bound. All right, so imagine if we have this, for example, if this negative a negative symbol was not there, then these two would be equivalent. However, think of everything that was positive. What happens to everything that was positive? Now that we multiply by negative, everything that was positive becomes a negative. So this graph will now go through, instead of 0, 1, what is that point going to be? 0, -1. And it's still going to approach and get closer and closer to the line y = 0. All right, but that's the main idea. Everything that was positive now becomes a negative. So in a way, you can think this graph, how was it transformed to become, let me redo that. How was this original parent graph transformed to become this one? And the idea is everything that was positive now become a negative. We've seen that before with quadratics and that, or other functions, and that's known as a vertical reflection. It got reflected vertically. And same idea, if we know what 2 to the x looks like, then we know that the reflection is that before we had the point 0, 1, but now we have the point that is common as 0, -1, since it was reflected vertically across the x-axis. And then we know that it goes towards negative infinity without bound instead of positive infinity. And getting closer and closer to 0. What's the equation of that line? It is y = 0. So hopefully you understand that first transformation, all right? And I will write it in. This is a vertical reflection. We've seen that in other functions in their graphs, vertical reflection. And that just means multiplying the parent function by a -1. Okay, cool. And let's see another transformation of it. Let me do that with a different color. Let's separate these two ideas from each other. And this is the last transformation on this video. Cool. So imagine this parent function, y = 2 to the x. Do we know how to sketch that really quickly? Oh, by now we do. This 0, 1 as the common shared point or y-intercept. This goes towards infinity. This one goes towards 0, but never reaches it. That's why it approaches the line y = 0. And I want you to see the similarities and difference between this equation here and this one. How did this equation become that equation? Well, if the 5 wasn't there, pretend the 5 wasn't there. Then they're the same, right? 2 to the x equals y = 2 to the x equals y = 2 to the x. But that was not the case. We have 5 times something. So before, when the original parent equation had a y-intercept of 0, 1, what's going to happen? Ignore the 5. What's the original y-intercept of 2 to the x? It is 0, 1. But what happens when we multiply that by 5? It is going to become 5 times larger, meaning instead of 0, 1, it is going to become 0, 5. So I want you to see what happened there. And when x is positive, that's going to grow without bound easily, because now we're still multiplying them by 5 and doubling every time. And then here it's still going to go towards infinity, maybe just a little bit slower, but not that much. It's still going to go towards infinity and have the line y = 0 as its boundary line. When you sketch these yourself, I highly encourage you to write the equation and draw the dashed line as the boundary, as well as its equation, just so you have a better visual of what you're actually representing or graphing at that time. Don't just graph for the purpose of graphing. So think of this the same as the previous ones. We're going to ignore the 8. Do we know what the y-intercept of 3 to something is? Yes, we do. It is 0, 1. But what happens when we multiply that by an 8? It becomes 0, 8. So 0, 8 is now the common or shared point or y-intercept. And as x gets larger, of course, this is going to go towards infinity very quickly. And when the exponents become negative, this is still going to approach 0, just a little bit slower. Maybe 8 times slower because of that factor of 8, but it will still do that. And the boundary line is still y = 0. If you're confused about this, ask somebody a question or let me know in the comments, but hopefully it's very straightforward from here. Let's do 2 or 3 more examples. I think we just have 3 more. Same idea, just different notation. Notice how before I use 5 times 2 to the x and 8 times 3 to the x represented with a dot product symbol. But a lot of times it's more convenient to use for these exponential equations, it's more convenient to use parentheses, and we will see it like that. So we still think 10 times 4 to the something. Ignore the 10. What's the y-intercept of 4 to the something? It is 0, 1, but now it's 10 times larger. So we're going to say, all right, this is 0, 10. Not drawn to scale, but we can label that point as 0, 10. But it doesn't change. We haven't done much to it. It's still going towards infinity, and it is still going towards 0. What's the boundary line again? That's a really sketchy boundary line, but it's all right. Y equals 0. That's why it's a sketch. There it is. I think I have everything needed at this point for this quick sketch. This next one is 3 times a to the something. Let's ignore the 3. We have a to the something. What's the y-intercept? It is 0, 1, but now it is 3 times larger. So this one's right here, 0, 3. And same idea, no other transformations. Therefore, this is getting really large as x gets larger and larger towards infinity without bound. But when the exponents are negative, it still approaches 0, just at a little bit slower pace. Same equation, y equals 0. Check and compare my work to yours. The main thing that changes is that common point based on the transformation, all right? The next one's going to have 2 types of transformations combined in itself, the 2 things that we've explored at this point. Now I notice this negative in front of the expression, meaning it's going to reflect downwards or vertically. But there's also if you don't know what it is called at this point, this is a vertical stretch as well, because the y value is getting stretched by a factor of 5 or 8. And hopefully those terms are not new to you, because we have explored those with quadratics. Otherwise, ask questions or let me know in the comments that you need help with transformations, and I'll make a special playlist of transformations for you. Okay, great. So then we have the last one. It involves those 2. Remember that originally it would be 0, 4, somewhere right here. But because it's negative 4, then we have 0, negative 4. The boundary line doesn't change. It still remains y equals 0. But remember that everything that was positive, normally it would be this type of graph as the previous 2. But when you multiply by negative, everything that was positive now becomes a negative. Let me redo that. There we go. That one's going really fast. Oh, this is the more difficult one. But something like this, towards 0. This is going towards 0. And this one's going towards negative infinity in this case, whereas before it was going towards positive infinity, growing without bound. So there are 2 transformations on our parent function, very easily displayed. If you're familiar with transforming quadratics or other types of functions, then this should make a lot of sense to you. Otherwise, if this is your first or one of your first few exposures to this type of ideas, please plant it in your brain, because it will help you transform other equations, such as I don't even want to mention them. Any parent function that you can think of, all right? That's not the point of this video. So at this point, go enjoy the rest of your day. Eat some good food. Take a nap. Do some more math problems. Whatever you like, go and enjoy it. I'm going to record another video so that hopefully you listen to me talk about some more math soon, all right? Peace out, guys. Late.